Dear friends, hearty welcome to the online problem solving session organized by Maths Aspirants. Actually, today is the second part of the group theory session by Mr. V. Adithya, a research scholar from ISI Delhi. Adithya did his MSc from 𝚑𝚎𝚊𝚑𝚑 and currently pursuing PhD at Indian Statistical Institute, Delhi Center. I would like to express my sincere thanks and gratitude to Adithya for being with Math Aspirants. I welcome everyone to this problem solving session. Welcome, Adithya.
Thank you, sir. Thank you for the opportunity once again. So, as sir told, this is the second session. So, we'll try to solve many more problems related to group theory in this session. In last session, we did around 15 problems. So, hopefully, we are able to do more in this session. Anyway, so let's start. So, first, last time when we worked on some basic group problems and homomorphism problems. Now we are starting with silo subgroups and other things. Yeah. So for any prime number P, we have NP of G denote the P silo subgroups, number of P silo subgroups. So which one of the following is true for a group of order 2024? And this is a question from previous year GATE, as someone could have told by the group order. Anyways, so the first thing we need is the prime number factorization of 2024 in order to start with any such problems. So we have mod G is 2024, which is basically, which is it, 2 cube. So 8 divides 2024, you can see that. So if you divide it by 8, 2000 is 250 times 8 and 24 is 3 times 8. So you would get 253. Right? And now from there in the options, you can easily say they're asking about 11 and 23. And if you check, 253 will actually be 23 into 11. So you can just write this as 2 cube times 11 times 23. So this is the first step. So now the next. What are the silos theorems? Let order of G be n, which is basically P power R times M, where GCD of P and M is 1, which means P and M are coprime. So in this case, what do we have? Then NP of G is congruent to 1 mod P and NP of G divides M. So these are the two important things about the number of P silo subgroups. So we can use that here. First, we'll start with 11. For P equals 11, you will have you will have mod G is 11 into 8 times 23. Right.
Sir, here NP of G must divide N or M?
It must divide N in general, but since we have NP of G is congruent to 1 mod P, it's enough it divides N. Yeah. Because it definitely won't, its coprime would be.
Yes, yes.
Yeah. So you have 8 into 23. So now you have N11 of G is congruent to 1 mod 11 and N11 of G has to divide 8 times 23. And using these two, you can say N11 of G is either 1 or 23. Both are possible. Now we can also check for P equals 23. We have N23, we have mod G is basically 23 times 8 into 11, which is 88. So N23 of G is congruent to 1 mod 23 and N23 of G divides 88. So from these two, you can say N23 of G has to be 1. So the correct option is B. Is this okay? Okay, let's move on to the next question. Yeah. Let G be an abelian group of order 35. Let M denote the number of elements of order 5 in G and N denote the number of elements of order 7 in G. Then the value of M plus N is? That is the question. So, how can we solve this? Again, we'll use 𝚠𝚎's theorems.
Sir,
First
is
to
it
see-
10? Is it 10?
It is 10.
Yeah.
Good. So again, how we do is we use 𝚠𝚎's theorems here.
Yes.
So we have mod G is 35, which is 5 times 7. So we have N5 is the number of 5 𝚠𝚎 subgroups. G I am avoiding here. N7 is the number of 𝚠𝚎 subgroups, 7 𝚠𝚎 subgroups. So we have, what do we have for N5? N5 is congruent to 1 mod 5 and N5 divides 7. You can easily see N5 is 1. Similarly, N7 is congruent to 1 mod 7 and N7 divides 5 would give me N7 is 1. So let this unique subgroup be H. H is the 5 𝚠𝚎 subgroup. A is the 7 𝚠𝚎 subgroup. Yeah. So now next, what can we say? These are unique. So there won't be any other subgroups of order 5 or 7 because any subgroup of order 5 is a 5 𝚠𝚎 subgroup and any subgroup of order 7 is a 7 𝚠𝚎 subgroup. And since it's unique, that's exactly 1. So now order of H is 5, which implies what is M? M is basically the number of elements of order 5. So any group of prime order is cyclic. So H is cyclic. So the number of elements of order 5 would be phi of 5, which is basically the Euler 5 function. So this is basically 5 minus 1, which is 4. Similarly, N equals phi of 7, which is basically 7 minus 1, which is 6. This implies M plus N is 10. So is this okay?
Okay, sir.
Yeah. Let G be a group of order 39 such that it has exactly one subgroup of order 3 and exactly one subgroup of order 13. Then which of the following is true? So what are we given? Order of G is 39, which is again 3 times 13. Again, we'll try to use the 𝚠𝚎's theorems. N3 is the number of 3 𝚠𝚎 subgroups. N13 is the number of 13 𝚠𝚎 subgroups. We have N13 is 3 is congruent to 1 mod 3.
Sir,
And-
sir,
Yes.
it is, I think it is 39 into 3. I think it's congruent to isomorphic to Z3 cross Z13 because here M and N are GCD of 1. That is why G should be cyclic.
Okay. Fine. It is correct. G is cyclic. but we can't directly use that G would be Z3 cross Z13, which is actually true.
No, sir. Here it is. I am applying that if the G is commutative or abelian, then I can say this. But here, not necessary. G is just abelian also necessarily.
Yeah. So we can actually show G is cyclic using Ksylos's theorem. So I'll just show. Using the given conditions, we can actually show G is cyclic. Anyways, so this implies N3 equals 1 or 13, because 13 is also congruent to 1 mod 3. Here, of course, you will have N13 is congruent to 1 mod 13, and N3 divides 3, sorry, N13. So N13 has to be 1. So N13 is 1 is fine, but here N3 is 1 or 13, but we are given that it has exactly one subgroup of order 3. Yeah. So by given condition, N3 is 1. And let's call this unique subgroup to be H and this unique subgroup to be K. And this is another theorem. Again, if the P-Silo subgroup, I'll use the short form PSSG, which stands for P-Silo subgroup, is unique, then it is normal. Right? So we know this, that if the P-Silo subgroup is unique, then it is normal. So both H and K are normal. Right? Here H and K normal, order of H is 3, order of K is 13. Right? Now, H intersection K is trivial. I mean, one can easily show that H intersection K is trivial. I'm just leaving it now. So here is one more small exercise which you can try. Let HK be normal subgroups such that H intersection K is trivial. Then HK equals KH for all H and H K. So try to work this out. This is quite simple to work out. So, or if you want, I can do it. Anyways, so H is a subgroup of order 3. So order of H is 3, which implies H is generated by H because it's cyclic. Any group of prime order is cyclic. Order of K is 13, implies K generated by K. Now, order of H is 3, the element, and order of K is 13. And now by this result, they commute. Yeah, so now since HK equals KH, order of KH is basically what? LCM of order of H and order of K. We know this result only if K and H commute. If K and H are of finite order and they commute, then order of K, HK or KH is the LCM of order of H and order of K. This is basically LCM of 3 and 13, which is basically 39. This implies HK belongs to G and order of HK equals 39, which is basically order of G. So basically G is cyclic. Is everyone okay with this?
Yes, sir.
Okay. Let G be a subgroup of, let G be a group of order 30. Which of the following statements is necessarily true? G is abelian but need not be cyclic. G is cyclic. G cannot have more than 7 subgroups of order 5. And G can simultaneously have 1 subgroup of order 2, 5 subgroups of order 3, and 6 subgroups of 5. So if G is a group of order 30, is G abelian? Are every group of order 30 abelian? Or do we know any group of order 30 which is not abelian? D15 or D30, right? It depends on which notation you use. Some use Dn or some use D2n, which is basically the dihedral group. So, dihedral group. So if it's not abelian, then it's definitely not cyclic. So B is also wrong. So we just have to look in between C and D. So what does C say? It's asking about groups of order 5. So order of G is 30, is basically 2 into 3 into 5. So now N5. What are N5 is the number of 5-cycle subgroups. So what are the conditions we have on N5? N5 is congruent to 1 mod 5 and N5 divides 6, 2 times 3. So N5 equals 1 or 6. Right. So you can have either 1 5-cycle subgroup or you can have 6 5-cycle subgroups. Right. So, and the silo subgroup are of order 5 and any subgroup of order 5 is a 5-cycle subgroup. So you can have a maximum of 6 subgroups of order 5. Right. So C is actually 2. G cannot have more than 7 subgroups of order 5, which is 2. What about D? G can have 1 subgroup of order 2, 5 subgroups of order 3, and 6 subgroups of order 5. What do we have? Let's check the other, N3. We have N3 is congruent to 1 mod 5, sorry, 1 mod 3, and N3 divides 10. So you can have N3 equals 1 or 10. These are the only 2 possibilities. So, in no way G can have 5 subgroups of order 3. It can either have a unique subgroup of order 3 or it can have 10 subgroups of order 3, 10 distinct subgroups of order 3. So D is false.
Sir, please repeat here.
Which one? The last point?
Last, yes.
So basically it's asking if this statement is true. G can have 1 subgroup of order 2, 5 subgroups of order 3, and 6 subgroups of order 5. 1 subgroup of any prime order is always possible. Right? So that
Yes.
it is possible. We have also seen 6 subgroups of order 5 is possible. Because of this. So now the only thing left to check is 5 subgroups of order 3.
Not
So
possible.
any subgroup of order 3 would be a 3-cycle subgroup. because
Yeah.
3 is the maximum power dividing 30. So check N3. N3 is congruent to 1 mod 3 and N3 divides 10. So the only possibility you have is N3 is 1 mod 10. So N3 divides 10 gives you N3 is 1, 2, 5 mod 10. And now N3 congruent to 1 mod 3 restricts it to 1 mod 10. Excuse me.
Yes.
So yeah. So
Sir, for
G can
cancelling,
never have 5 subgroups of order 3.
yes, sir, cancelling for first option, it is diagonal. If we take n is equal to 15, then 2n of d2n is equal to 30, and diagonal group of always
Yeah,
non-abelian.
that's what I told. The first two options have been cancelled out by dihedral groups.
Okay.
So whatever you told, D15 or D30, it's called the dihedral group. Right. So you can easily eliminate the first two options. So any group of order 30 is not abelian. Example, dihedral group. And if it's not abelian, then it's definitely not cyclic. So again, dihedral group. Anyways, true or false? This is from TFR. There exists an non-abelian group of order 26 such that every subgroup of G is abelian. Okay. So now again, let's look at order of G. Is 26 is basically 2 times 13. Here in 2 and 13. So here, of course, they are meaning every subgroup in the sense proper subgroup. Same as that. Because if G is not abelian and you take G itself as a subgroup, then it is not abelian. So the statement becomes false. Trivially. Even in this case, we don't know whether it's true or false, but in this case, we can at least try. Right? So we have N2 is congruent to 1 mod 2 and N2 divides 30. This implies N2 is 1 or N2 is 13. Here we have N13 is congruent to 1 mod 13 and N13 divides 2. This means N13 is 1. So now, no matter how many silo subgroups you have, the two silo subgroups H will have order 2. So it's a prime order subgroup. So it's necessarily cyclic, hence it's abelian. Right. Similarly, any the unique K, which is the subgroup of order 30, that will also be cyclic, hence abelian. So no matter what your group G is of order 26, every proper subgroup of it is abelian. Because it's either of order 1, 2, or 13. And 1 is trivial, 2 and 13 are prime order, so it is cyclic, hence abelian. So now, the question just reduces to, is there a non-abelian group of order 26? True or false? It's true if you take the dihedral group D30. Again, 26 is even. So this statement is actually true. Okay. True or false? There are exactly 10 abelian groups of order 2025 up to isomorphism. So again, this is again a formula which you can remember. So suppose you want number of groups, abelian groups up to isomorphism of order n. So now let n be p1 power e1 pr power er. This is the prime factorization. So what will you get? This is equal to what's the rotation? I'm not sure. So basically, this is basically product I equals 1 to R, number of partitions of EI. So we all know what is partitions, right? We use the partitions when we look at symmetric groups. So how can you partition 4? 4 can be partitioned as 4, 3 plus 1, 2 plus 1 plus 1, 2 plus 2, and 1 plus 1 plus 1 plus 1. So 4 has 5 partitions. So what are number of partitions for 3? 3, 2 plus 1, 1 plus 1 plus 1. There are only 3 partitions of 3. Right. So and we are taking the partitions of EI, the powers. So this formula actually comes from the what is it called? Theorem on finite abelian groups, which is done in the algebra course whenever you do rings and modules. So fundamental theorem of finite abelian groups. So I'm not getting into the proof. This can be derived from there. So I'm just giving the formula directly. So first here we have n equals 2025. So what's the prime factorization of 2025? 2025 is actually 45 square, which is basically 9, which is 3 square times 5 the whole square, which is basically 3 power 4 times 5 square. This is the prime factorization of n. So number of partitions of 4 is 5, as we have seen here. Number of partitions of 2 is basically 2. For 2, you'll basically have 2 and 1 plus 1. So the number of abelian groups up to isomorphism of order n is basically 5 times 2, which is 10. So this is actually 2. So is this clear? Okay. Again, another true or false question. Let G be a group of order 361. Then G has a normal subgroup H such that G mod H is isomorphic to H. So how can we go about this question? So firstly, we will try to prime factorize 361. Okay, 2 is the answer from one of the participants. Let's see. So order of G is 361. which is basically 19 square. So it's a group of order p square, where p is a prime, odd prime. G is a group of order p square with p prime. So now time for first basic. So if G mod H is isomorphic to H, mod of G by mod of H is equal to mod of H. This implies mod of H, the whole square is 361, which implies mod of H is 19. So H has to be a subgroup of order 19. So now we obviously know G has a subgroup of order 19. Yeah, that's always true. So this is just one way. You can't just be like, if since we have a subgroup of order, yeah, so that basically, so now G has a subgroup of order 19. Right? Right? Because 19 is a prime number, and we know for any prime dividing the order of G, that exists an element of that order. Right? So we'll have an element of order 19. So that will generate a subgroup of order 19. Right? So both G mod H, so this implies order of K is 19. And is K, what is it? Normal. Here is one more exercise. G is a group of order p square with p odd prime. Even if p is 2, it doesn't matter, because 2 square is 4 and every group of order 4 is abelian. Anyways, but you can try to prove this for odd prime, then G is abelian. So if G is abelian, any subgroup of G is normal. So K is normal. So G mod K is a group, and order of G mod K is also 19. So both of them are groups of order 19. We know 19 is a prime, so they both have to be isomorphic. Because there's only one possible group of order 19, which is the cyclic group Z19 or Z mod 19Z, and both of them are there, which implies G mod K is isomorphic to K. So it's actually true. Is this fine or? Okay. Let G be a group of order 75, which has an element of order 25. Then the number of elements of order 5 in G is. Again, I would suggest to use 𝚬's theorem. So again, order of G is 75. It will be 3 times 25, which is 5 square. So N3 and 5. N3 is congruent to 1 mod 3, and N3 divides 25. N5 is congruent to 1 mod 5 and N5 divides 3. N5 is 1. N3 is, it's either N3 can be either 1, 5 or 25. 5 is not congruent to 1. 25 is congruent to 1, so it can be either 1 or 25. Anyways, but we are dealing with the number of elements of order 5. So number of elements of order 5 have nothing to do with N3. Because whatever group you get in N3 will be a subgroup of order 3. And it has nothing to do with elements of order 5. So let A be the unique 5-silo subgroup of G. Right? And let AG be an element of order 25. Because we are given that we have an element of order 25. Firstly, A has to belong to K. Right? And since order of A, which is 25, is basically the order of the subgroup, K is basically cyclic. This implies number of elements of order 5 in G is basically equal to number of elements of order 5 in K. K is cyclic of order 25. So if G is a cyclic group of order n, for any D divides n, the number of elements of order D is phi of D. This is basically phi of phi. And phi is the Euler-Tolsche function. Basically 4. So is this clear? Nice. Yeah, so this is an interesting question. This is from the GATE exam of previous year, 2024. The number of non-isomorphic finite groups with exactly 3 conjugacy classes is equal to what? So we have 3 conjugacy classes, which means we can use class equation. So yeah. So we have order of G is basically n. So firstly, are there any finite groups that you can think of with exactly 3 isomorphic 3 conjugacy classes? So first, let G be an abelian group with order of G equals n. Then the number of conjugacy classes of G is how much?
1 plus 1 plus
Yeah.
n.
So it can be 1 plus 1 plus 1, so on. So the number of conjugacy classes is m. And order of G equals n is 1 plus 1 plus This is the class equation n times. Isn't it? So immediately when we want three conjugacy classes, we can think of abelian group of order 3. What's an abelian group of order 3? Z mod 3Z. So Z mod 3Z has exactly three conjugacy classes. Right. So anyways, let's try to solve this, prove this. Like check if it's the only one or is there anything else. So now n. So you have to write it as something plus something plus something. Right. Because the class equation will have exactly 3 parts. It has exactly 3 conjugacy classes. We always have a 1 at the start because the identity always belongs to the center of the group. And that always gives us a 1, which is basically the conjugacy class of identity. So the remaining 2 we don't know. Let's have it as 1 plus A plus B. Assume A is less than or equal to B. Right. Because one of them has to be less than the other. So this is like, this assumption is like without loss of generality. Anyways, so what else do we know about the parts of the class equation? So we know A divides
N.
A divides N and B divides N, right?
Yeah. Yes.
So A divides N and B divides N. This implies A divides 1 plus A plus B and B divides 1 plus A plus B. So now this implies A divides 1 plus B because it already divides A and B divides 1 plus A, right?
Yes, sir.
Now B divides 1 plus A implies B has to be less than or equal to A plus 1, right?
Yes, sir.
And you have A is less than or equal to B. This implies A less than or equal to B less than or equal to A plus 1. This implies B equals A or B equals A plus 1. These are the only 2 possibilities we have. So now what happens when B equals A? Now we'll use the other part. We have B divides 1 plus A. Sorry. B divides 1 plus A we have already used. So we have A divides 1 plus B. B is A. This implies A divides 1 plus A. This implies A has to be 1. Right? This is B. This implies order of G equals 1 plus 1 plus 1. So this basically G is Z mod 3Z. Right. So now B equals A plus 1. We have A divides 1 plus A plus 1. This implies A divides A plus 2. This implies A divides 2. This implies A is 1 or A is 2. Now we have another subcase here. A is 1. If A is 1, then B is 2 and order of G will become 1 plus 1 plus 2 is equal to 4. However, every group of order 4 is cyclic. Sorry, abelian. Every group of order 4 is abelian. Right.
Yes, it
So
is
this gives us
Z4
a
or plain
contradiction.
group.
Because you cannot have 1 plus 1 plus 2. Because for any group of order 4, it will be 1 plus 1 plus 1 plus 1. So this is not possible. Now the other case, if A equals 2, B equals 3, and order of G is basically 1 plus 2 plus 3 is 6. So is there a group of order 6 which admits this class equation 1 plus 2 plus 3?
S3.
S3. Because for Z6, so if a group is of order 6, then it's either Z6 or S3. Z6 is abelian, so it will be 1 plus 1 plus 1 6 times. For S3, you can check it will be 1 plus 2 plus 3. So G is isomorphic to S3. So you have basically got it. So we have actually proved that if it has 3 conjugacy classes, then it has to be Z3 or S3. So that's actually 2. Is this clear?
Yes, sir.
Okay. Let G be a finite group containing a non-identity element which is conjugate to its own inverse. Then which of the following is true? A. Order of G is necessarily even.
Excuse me, sir.
Yeah.
Sir, could you please explain how is it to like the previous problem?
Okay. So we are given G has 3 conjugacy classes, exactly 3 conjugacy classes. So it will have 3 parts in this summation,
Yes, sir. Yeah.
right? And we already know one will come because that corresponds to the conjugacy class of identity element.
Yes, sir. Yes, sir.
So we have remaining 2, let that be A and B.
Okay.
Yeah, without loss of generality, we can assume A is less than or equal to B.
Yes, sir. Yeah. Yeah. Got it.
So now what are the other properties of this class equation? All these individual terms divides the order of the group.
Yes, sir. Yeah. Yeah.
So we have A divides Z and B divides Z. So we have A divides 1 plus A plus B and B divides 1 plus A plus B. And since A already divides A, we will get A divides 1 plus B and B divides 1 plus A.
Yes, sir.
Right. So now since B divides 1 plus A, B has to be less than or equal to 1 plus A.
Yeah. Yes, sir.
And we already have A is less than or equal to B. So we have this bound like A less than or equal to B less than or equal to A plus 1. So you can have B is either A or B is either A plus 1.
Yes, sir. Yeah. Yeah. Got it.
So now we have 2 cases, B is A. So now we have A divides 1 plus B. Substituting B equals A, we have A divides 1 plus A, which means A has to be 1, and which is the same as B. So G is basically 1 plus 1 plus 1, which is basically the group of order 3.
Is that 3? Yeah.
So now B equals A plus 1. We have A divides 1 plus B. So that is 1 plus A plus 1, which is A divides A plus 2, which means A has to be 1 or 2.
Yes.
So if A is 1, then B is 2, and you will get this class equation 1 plus 1 plus 2, which is basically 4. But we know every group of order 4 is abelian. So if they have class equation, the class equation has to be 1 plus 1 plus 1 plus 1. So this gives us a contradiction. We can't have such a class equation.
Okay. Okay, sir. Yeah. 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 Got it, sir. Yeah. Okay.
So now the other case is if A is 2, then B is 3, and order of G is 1 plus 2 plus 3 is 6. This is the class equation. And you can easily see this is the class equation of S3, this symmetric group.
Yes, sir. Yeah. Yeah. Now I got it, sir. Like I
Yeah.
had a doubt on this part, this contradiction, but now I got
The
it.
contradiction.
Okay. Yeah. 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 Yes,
Okay.
yes. Yeah. Okay. Thank you. Thank you, sir.
Yeah. Let G be a finite group containing a non-identity element which is conjugate to its inverse. And which of the following is true? The order of G is necessarily even. Or other things. So firstly, we can see the last two options have to be false. Right? Why does this have to be false? Why do C and D have to be false? Again, you need an element which is conjugate to its dihedral group property. So if an element and its inverse are the same, if A equals A inverse, they are definitely conjugate to each other, right? This implies A square is identity. Order of A divides 2 and we'll get order of A is 2 since A is non-identity. Right. So if basically your group has an element of order 2, then you will definitely have an odd identity element which is conjugate to its inverse. Right. So you can find a group of even order which is not cyclic and not abelian. So this is again by dihedral groups. For dihedral group, you can show that C and D are not true. So is this part fine?
Sir, I cannot got it because here how cancelling this option. If A is equal to A inverse, then order of 2 it is clear, but how it
Yeah.
is relating
If
to
A
the
is A inverse,
yes.
an element is conjugate to itself, right?
Oh, yes, because A is equal to A inverse conjugate means here where there exists a term, suppose G A is equal to G A inverse G, or
Yeah, you can
G
use
A G inverse
identity.
is G inverse is equal to A inverse, something like that.
Yeah.
And using property of abelianness, we are cancelling those G element. Okay, and that is why A is equal to A inverse.
What?
If we use property commutative property, then then conjugate element, order of conjugate element, and this side is same because G are going to cancelling.
Yeah. So the first thing we are saying is, if we have an element of order 2, right? If A is an element of order 2, then it is conjugate to its inverse, right?
Yes, sir.
If you have an element of order 2, which is A square is E, A is A inverse. So A is definitely conjugate to itself. So A is definitely conjugate to its inverse, right?
Yes, sir.
So if your group has an element of order 2, you have a non-identity element
Yes,
which is
yes.
conjugate to its inverse.
There is a element in the dihedral group which is element generated by reflection and not abelian. That is why cancelling part and part.
Yeah, that's why part C and D go.
Okay. Thank
Because
you.
of the dihedral
Proceed.
property.
Yes.
Yeah. So now, what about the other part? What can we say about the order of the group? Does it have to be even or not?
Sir, if we take it is order even and proceeding.
No, we are trying to show it has to be even or not even. So let's try. So now let X in G be the non-identity element such that X is conjugate to its inverse. I'm just using this tilde for conjugation. First case, if x equals x inverse, then order of x is 2, which divides order of g. This implies order of g is even. Is this case clear?
Yes, sir.
Yeah. So now case 2 is if x is not equal to x inverse. So what can we do in this case?
Sir, x not equal to x inverse for all x.
No, for this particular x, which
Yeah.
has the property that it's a conjugate of itself. Yeah, so now we have x is conjugate to x inverse. So we have C of x equals C of x inverse. C basically denotes the conjugacy class. So the conjugacy class of x and x inverse are the same because they both are conjugate to each other. Right. So now consider the map phi from G to G given by phi of x equals x inverse. Okay, x I'm already using. Phi of G equals G inverse. This is not a homomorphism, but this is just a set theory map. It's just a map. Right. So this is basically a bijective map. Right. So this is basically a bijective map on G. And we always know for any G in G, the image of the conjugacy class of G with respect to this map is basically the conjugacy class of G inverse. Right. This you can show because you take any x in G, x in CG. Okay, we are already using x. So if we take any h in CG, and then you can show phi of h is in CG inverse. Because if h is conjugate to G, h inverse is conjugate to G inverse. We're taking inverse on both sides. So now in our case, since these both are equal, phi from Cx to Cx is a bijective map. Yeah. Yeah. So now, sorry, even I'm not sure how to proceed from this part. Anyway, so I'll try to, even I'm stuck, I guess. So the answer is order of G is even, just in case if you want it. But I am stuck at this point. Yeah, class of X should be equal to class of X inverse. That's true. Anyways, so what I would try, I'll try to solve this, and if I get the solution, I'll post it. But now I think we can move to the next question because we are running out of time. Is that fine? Okay. Sorry for this, but yeah. Anyways, so now consider the following statements. Let G be a group and let H be a subgroup of index 2. Then, so the bracket G comma G denotes the commutator subgroup. Everyone knows what is the commutator subgroup?
No, sir, I don't know.
Okay. So let X comma Y belong to G, then we denote X comma Y, this thing. This is for the elements, not the group. This is basically the element X inverse Y inverse XY. Right? So now the commutator subgroup G comma G is defined to be the subgroup generated by X comma Y, such that X comma Y is a G. This is the subgroup generated by all such elements, because you can see just this set containing all the elements will not form a subgroup. So we are taking the subgroup generated by all these elements. So now, since you don't know, there are some properties. I don't know if we'll use these properties here, but anyways, this is a normal subgroup. And the quotient is abelian. Right. So this is one of the properties. And there is one more property which I think I might be using. So I'll just put it out. If H is a normal subgroup, such that G mod H is abelian, then the commutator subgroup is contained in H. Right. So these are some of the important properties of the commutator subgroup, and all of them are quite easy to see. So I would ask you guys to try to show how is it a normal subgroup and why is the quotient. The quotient is abelian, and the second property, they follow quite easily from the definition of the commutator subgroup. Yeah. So anyways, so now let's start with the first A part. So H is a subgroup of G such that order of H, sorry, the index of G mod H, it is a subgroup of index 2. What do we know about subgroups of index 2? They're always normal,
Normal.
right? Any subgroup of index 2 is normal. This implies H is normal. Also, what is the order of G mod H? Which is basically the index. And this is 2. This implies G mod H is abelian. So, the commutative subgroup is contained in H. So, A is actually 2. Is this okay?
Yes, sir.
Okay. So now, what about the other? So let's look at the other part. So what are we given? P is basically H is a subgroup of G and the commutator subgroup is contained in H, right? So now we have to show that we have to check if H is normal or not. So what do we have to show? Let G belongs to G and H in H. What do we want to show? We want to check G and G inverse belongs to H. Right. So we know GH, G inverse, H inverse belongs to the commutator subgroup. Right. Which is contained in H. This implies GH, G inverse, H inverse belongs to H. Now H is also in H and this is also in H. So multiply by H on the right side. This implies GH, G inverse, H inverse times H belongs to H. This implies GH, G inverse belongs to H. So H is normal. Is this clear?
Yes.
Yes, sir.
So A and B are both true. Right?
Yes, sir.
Okay. Consider the following statements. There exists a proper subgroup G of Q such that Q mod G is a finite group. There exists a group G of Q plus such that Q mod G is isomorphic to Z plus. Okay. Okay. So let's start with the first part. So we'll try to either show this is true or we have to show it's false. So showing false might be difficult because first we'll have to find out all the proper subgroups of Q plus and then see if the quotient is finite. We can check if it's true by assuming this and seeing if we are able to get any contradiction. Let G, it's a proper subgroup, proper such that Q mod G is finite. So I'll just take this order to be n, which is finite. So now for any A, Z, for any Q equals A by B in Q, A is an integer, B is a natural number. Right. A by P, Q. This is a quotient. This is an element of Q mod G. Right. A by B times G. Right. This implies A by B times G, the whole power n. Right. Since it has order n, this is equal to G. Since order of Q by G is n. So what do you get from here? Here it's quotient with addition. So this would just be A by B plus A by B plus A by B n times G is equal to G. This implies n A by B belongs to G for all A in Z, P in natural. Right. So now you can write every rational number in this form. Every rational number can be written as n into A by B for some integer A and for some natural number B. Like if it's of the form P by Q, you can write it as NP times NQ, and you can take A to be P and B to be NQ. So this is fine, right? So this actually implies G equals Q, which gives us a contradiction because we are assuming G is proper. Did everyone get this proof?
No, sir, I am
Okay.
I'm not getting now for any Q is equal to A by B from this line.
So till here you got?
Yes.
Till this part you are fine?
Yes,
Okay.
it is belongs to G for all F and B, and
Yeah.
that is and
So now,
every rational number can be put in this form. Okay.
Yeah, every element of this form belongs to G, right?
Yes.
Now I'm saying every element of Q will have this form.
If it is true, then G will
G will be
all
Q, which will give us a contradiction, right?
yes.
So now I am saying every element of Q is of this form. So now let P by Q belong to Q, right? P by Q is an element of Q. Then P by Q can be written as NP times NQ. Both are same. So now NP by NQ is of this form, right? Is it clear or?
Yes, but here the coefficient of B is 1, but here n.
What? I just want B to be a natural number.
Okay.
Right.
Yes. Yes.
So that's it. So this implies Q. So this implies G equals Q, which will give us a contradiction. Right. So the first statement is false. So what about the second statement? Right. So now suppose G is a proper subgroup such that Q mod G is isomorphic to Z plus. Right, basically integers. And let phi from Q mod G to Z be an isomorphism. Right.
Yes, and the generator of Z is 1. Yes,
What?
generator of
Yeah,
Z
Z is
is
generated
1
by
and
1.
minus 1. And that is of no finite order, I think.
Yeah.
And this part Q by G, I think it is a order of finite order.
Every non-identity element of Q mod G has finite order? No,
Order.
I'm not sure. But we can use this that let pi from Q to Q mod G be the natural surjective map.
Yes.
Right. This implies phi compose pi from Q to Z is a surjective homomorphism. Why? Because both phi and pi are surjective.
Yes.
So now the question boils down to whether there is a surjective homomorphism from Q to Z. So now let me take this to be some other f. So now since f is surjective, always play with the generator. There exists a in Q such that f of a is 1. Then 2 times f of a by 2 is 1. Right. This is the property of homomorphisms. F of a by 2 plus f of a by 2 is 1. So which means 2 times f of a by 2 is 1. However, this is not possible in the. But f of a by 2 is an integer. So this is not possible. We can't have 2 times an integer be equal to 1, right? Is this part clear?
Sir, I think this is interesting point because this part, given part is pi, given part is pi, and you have defined pi, and then composing it would get reduced to the finding of surjective homomorphism from Q to Z.
Yeah.
This part is quite interesting.
No, because the thing is, quotient groups are always quite difficult to work with.
Yeah. And
Right.
I am intuitively thinking these G quotient by Q quotient by G, and it contains an element, at least one element which is mapped to the element of Z. One side order is infinite and one side order is finite. I'm thinking about that, but
Okay, maybe you can work something out from there. I'm not sure. But this is what I thought of, because whenever we are trying to work with, quotient groups, it's easier if we are able to shift into some groups which we are comfortable with, rather than still working on the quotient groups.
yes, Q and Z are well known. And
Yeah, Q and Z are groups which are much more comfortable to work with than Q mod G. Right. At least if G was something specific, we could have worked. Like if G was Z, Q mod Z we can work with. But Q is G is any proper subgroup of Q. So it's always difficult to work with such quotients. So that's why I thought of going on this route where we can get it to Q and Z. Anyways, yeah, so I'm done, sir. So I'm done for this session. So I hope we discuss some interesting questions.
yes, sir, I'm like to request I noticed that recently noticed that previous 2 or 3 years, last 2 or 3 years, they are choosing question from the group of Z modulo n. I think it is UN, and try to find whether this UN and UM for n and m are distinct integer. Are there isomorphic, or they are asking something related to
Okay.
this UN group?
So
But
we discussed
we are,
questions like this
yeah,
in the previous session.
yes. And sir, there are, I think there are no option to checking all those order of these UN element. But in case suppose U12 or U10, there are quite time consuming for checking those element of order of each element from UN to compare the surjectivity or injectivity or
Yeah,
homomorphism between two groups. Are there any yes? Are there any standard fact that we can use to reduce this problem in quite
see,
known
we
problem?
discussed this problem last time.
Yes, and due to network issue, I am not able to continue the last portion of this previous section. That is why I am missing.
Yeah. So basically, we discussed two questions with this.
Yes,
So we had this and this,
yes.
right? So basically, what we were doing was, the first part was to check whether U of n is cyclic. And
Yes.
this is where I gave the primitive root theorem, which is basically a very important theorem. This is basically U of n is cyclic if and only if n is of this form. It is either 1, 2, 4, p power e, or 2 times p power e whenever p is an odd prime.
So, and like, can it be proved using existing fact of already we have read?
Which this proof of primitive root theorem.
Yes.
I didn't prove the primitive root theorem, but you can find the proof of primitive root theorem in any element, in any number theory book. It's actually a number theoretic result.
Okay.
In number theory, any
Yes.
generator of UN is called a primitive root. So they prove this primitive root theorem there. So you can check that out. Yeah. You can check this in any book related to number theory. You will get the proof.
And if we memorize this result, then it will make help.
Yeah. First of all, memorizing results like this is like Lagrange's theorem. So it's like, okay. But the thing is, I wouldn't remember all the results, everything, but these are some important results which you can remember.
Yes.
Right. So once you know this result, now try to solve this question.
Yes. Yeah.
You know, U of I and U of 10 are cyclic, whereas U of 8 and U of 12 are not cyclic. So you can easily get it is the correct option.
Yeah.
Okay, thank you, Adithya.
Thank you, sir.
You may please turn off the presentation and
Yeah.
keep the video on. We can go for the feedback session.
Yeah.
Dear participants, now it is your time to share the feedback. Feel free to share your feedback.
Yeah. Firstly, I will just say one thing. I'm sorry I couldn't do one question today because I got stuck somewhere in between. That's fine. So I will try to solve that question and then I'll let you know. Yeah. So
Yeah.
that's
Yeah,
one
Adithya,
from me for me.
while sharing the PDF, I think you can include that.
Yeah, I'll include the solution and then I'll share so that it's yeah.
Yes, sir. It is very good, nice session, and I think the previous session quite a little bit less communicative rather than today's session. Today's session well smooth and all are staying well spaced. We understand and explore very much new topic and new type of solution. It is very grateful to all of you to take time from your hectic busy schedule to address our request. Thank you, and thank you, sir, for organizing such wonderful session.
Okay, thank you, Supratim Sandra. Yeah, Reshma.
Good afternoon, sir. I am Reshma. Currently, I am pursuing final year BSc students. Thank you for your first. I want to thank to connecting this section, sir. Your explanation, everything is very simple and effectively, which made all topics very easy to understand. And the concept you covered is very extremely useful and many problem solved in depth. And the TI4 and gate level problems you discussed very interesting. I enjoyed entire session truly. I'm little weak for this area group 3, so it is very incredible beneficial for me. It was truly wonderful and enriching section, sir. Thank you once again, sir, and more connecting section, sir.
Yeah, surely I'll try to conduct more sessions. Of course, next week there is TA for exam, if I'm not wrong.
Yeah, it's on December 14th.
So I won't be, and also I am traveling this week, so I won't be able to take one session before TFR. But maybe before gate we can try to have one or two more sessions. I'm okay.
Yes, sir. It will be very helpful.
Before gate and jam, we can definitely try to have one or two more sessions. Yeah.
Okay, thank you, Reshma, for the feedback. Yeah, others. It's Shabiba.
Hi, sir. I'm Shabiba, currently in the third year of my BSc. I don't know, I have always found group theory a bit challenging, but the questions you discussed in the class were very truly helpful. Thank you so much for your effort, and thanks to Vinod, sir, for arranging this wonderful class.
Thank you,
Thank
Shabiba.
you.
Good afternoon, sir.
Yeah.
Yes,
Sir, my name is Varada. So just like the previous class, I found today's session also extremely useful. Like as everyone said, your way of explaining things is like very easy to understand. So I genuinely enjoyed the class, and all the questions were also very interesting as well. So it helped me get different ideas on how to solve the questions. And yeah, actually, sir, when I got to know that Thursday's class got postponed, I felt very sad. But yeah, so glad to attend it today. So thank you so much, sir, for giving us your time and patience to solve our doubts. And thank you, Vinod, sir, for organizing this class.
Okay, thank you, Varada.
Thank you.
Hello, sir.
Yes.
Hello.
So I'm Archana. I have completed my BSc. I have taken a drop year for JAM. So I really enjoyed your session. Just like last class, it was very simple and your explaining was really nice. So personally, for me, group is very tough. Like in terms of understanding the definitions, I'm fine with it. But when you link different concepts, like being abelian is cyclic, so like all those concept linking, I don't know why I'm not able to take it all in. So is there any tip or something you can say? Like how, like for conjugacy classes, abelian, we have 111, like a lot of links are there between the groups. So I'm not able to take in. So is there any notes or something which I can refer, or any textbook in which I'll have a better understanding of the subject as in a core? Not
Okay,
only
so-
applicatively.
So majority of the, one of the standard references is basically the book by 𝚠𝚊𝚛𝚘 on abstract algebra, which actually
Okay.
covers a lot. So it also extensively covers group theory. So I'll definitely suggest you to look at it.
Okay,
That's
sir.
quite introductory. It's well written, and there are a lot of problems there which you can try solving. So regarding the results, whatever you told, the conjugacy classes for abelian groups and everything, these all just become part of our system once we start using this or do a lot of problems related to it. I agree.
Okay.
Remembering a lot of results is very difficult. Even me, I don't remember many of the results. But the thing is, once you know these main results, it's easy for you to get to the other smaller results quite easily. Like if you know
Okay.
what is the class equation, yeah, how it's
Yes, sir.
structured, what are the components of it. You
Yes,
could
sir.
easily see that if you take any element and if you look at conjugate Gx G inverse, if the group is abelian, you can exchange X and G inverse, so it just gives you back X.
Yes, sir. Yeah. Yeah.
Right. So it's just understanding the definition and then trying to work it out. So,
Okay, sir.
but anyways, regarding references, I would definitely suggest 𝚠𝚊𝚛𝚘 for starting. And then after
Okay,
that,
sir.
if you want to explore much more, I would suggest Artin's book, Michael Artin's book on algebra. It
So,
doesn't
sir?
Michael Artin.
Okay, sir.
So I'll just type it. The first one is 𝚠𝚊𝚛𝚘, and the second one is Michael Artin's book. So
Okay, sir.
these are the two books for algebra, which is standard, and it's used in many places for the courses as well. So you can try to work it out. And I guess you can get notes on group theory on like some something if you search for, if you want it for competitive exam purposes. There are
Yes,
many
sir.
books which you can search on the internet, which just
Oh,
gives you like, just the results without any proof or anything. Just for you
okay,
to
sir.
want to remember the results. Yeah.
Okay, sir. Yes. Thank you so much, sir.
Thank
I
you.
really enjoyed your session and hoping from more from your side. Thank you,
Thank you
Vinod,
so
sir, for
much.
organizing the session.
Okay, thank you, Archana. Yeah, any others? Yeah, 𝚠𝚒𝚘𝚗𝚖. So you are very actively involved in the session from the very beginning. It would be nice if you could introduce
Yes, sir,
yourself
yeah.
and say something.
Sir, actually, so I am 𝚠𝚑𝚘𝚗𝚗𝚑. So I am basically from Tamil Nadu, Tirur district. So I have completed my masters. So now I'm preparing for a NET GATE and all. So actually, I'm like really interested in algebra. So I had attended the last session as well. So today's session also was very nice. So basically, like those three problems, like from conjugacy classes and that commutator G comma G,
Yeah.
that problem, then that last problem. So Q by G,
Yeah.
so that
Quotient.
Z, yeah. So these three problems, like it was very interesting. I really enjoyed those problems. So
Yeah.
like,
Thank you.
so yeah. So you really inspired us. So we'll work. So we'll try to connect to you, sir. Thank you very much.
Yeah. Thank you.
Okay.
Thank you, sir. Thank you.
Yeah, thank you for your feedback. Others, if any of you would like to share a feedback, you can do it. Alagananda, Dharmendra, I think only few, only 10 people are there. Okay.
Yeah.
Yeah, but being a Sunday and people may have many other things.
Yeah.
Okay, Adithya, thank you very
Thank you,
much.
sir. Thank you,
for
sir.
this nice
One more
session.
thing I'd just like to say, like, if at any point I had, like, due to my cold, if it was not, if you are not able to understand, sorry for that. Due to Delhi winters, so completely, uh, I'm having cold now. So
Yeah,
yeah,
yeah. I thought from your voice, I seen that.
yeah. So that's what. So yeah. So if something was not clear because of that, sorry for that. Yeah.
Yeah, no. Your voice is perfectly audible, and the things the class went very nicely.
Yeah.
So thank you, Aditya, for taking all this effort apart from your.
Thank you so much, sir. One final thing, all the best to people here if you are writing for the TFR exam next week. If something which I have done helps you in the exam, I'll be very happy. Yeah, that's it.
Yeah, it's surely your session will be really helpful for all those who are seriously preparing.
Yeah.
The others can watch the sessions from the YouTube also.
Yeah.
So unable to attend the live sessions, we will
Sure.
provide it. So please update the PDF with the answer.
Sure, sir. I'll send you the PDF. Yeah.
So we can share it along with the recording.
Yeah.
Okay. Thank you, Aditya.
Yes,
And
thank you.
to participants. Let us wind up here.
Yeah. Thank you all. Yeah.